captions in English, please. So this is the 8th video of chapter 8. And it's going to be on empirical formula from reaction data. So we've learned up to now how to write the empirical formula from experimental data. This is also very similar. Here it's from reaction data, which may not be as easy at first. So a 2.23 gram sample of iron reacts with sulfur to form 4.15 grams of the metal sulfide. What is the empirical formula of the metal sulfide? So you have these amounts of iron and metal sulfide. So the given are 2.23 grams of iron that you react with sulfide, and you're producing 4.15 grams of the metal sulfide. So the metal sulfide is the compound, and we don't know its formula. And we want to find its empirical formula. So here, you cannot convert the mass of the metal sulfide into moles because you don't have its formula. You would need its formula. And that's precisely what you're trying to find. So you're given the mass of the initial iron sample. So the iron you made react with the sulfide. And so the mass of its sulfide after it has reacted with the sulfur. So the difference of the mass of the metal sulfide minus the mass of the iron will be the mass of the sulfur. So you can get the mass of the sulfur by difference here. So to find the mass of sulfur, subtract the mass of iron from the mass of the metal sulfide of the compound. And the difference will be the mass of the sulfur by itself. So the mass of iron is 2.23 grams. And the mass of the sulfur will be the mass of the metal sulfide minus the mass of the iron. And the mass of the metal sulfide is 4.15 grams of iron and sulfide bonded together, minus 2.23 grams of iron. The difference is 1.92 grams of sulfur. So that's how you get the mass of the sulfur. So now that we have our masses, we can convert the mass of each element to moles. So the next step is to change the number of moles of each element and determine the pseudo formula. So 2.23 grams of iron multiplied by 1 mole of iron over 55.85 grams of iron. That's the molar mass of iron, and we have the grams on the bottom, so we can cancel the units of grams of iron. Remember how the molar mass is found in the periodic table. So 2.23 divided by 55.85 is 0.039928, etc. Because we have a mass given with 3 sig figs, we'll keep 3 sig figs. So 0.0399 moles of iron. Let's find the moles of sulfur using the 1.92 grams of sulfur multiplied by 1 mole of sulfur over 32.07 grams of sulfur. That's the molar mass of sulfur. And we use it as a conversion factor with the grams on the bottom, so we can cancel the units of grams of sulfur. And 1.92 divided by 32.07 is 59869. So if we run this to 3 sig figs because of the given amount given with 3 sig figs, that's 0.0599 moles of sulfur. So we can then write the pseudo formula, and it will have those numbers of moles as subscript for each element. So it's going to be Fe 0.0399 and then S 0.0599. So next you divide each subscript by the smallest of the subscript, and here the smallest is 0.0399. So you do Fe 0.0399 over 0.0399. That's going to be a 1. And then for the sulfur, 0.0599 divided by 0.0399, it's 1.5. So we have this pseudo formula now of Fe1S 1.5. The empirical formula should have all numbers, you know. So the 1.5 here is a problem, and we need to multiply this formula by 2 to get rid of the 1.5, because by multiplying by 2, the 1.5 will be a 3, the smallest, whole number that comes after 1.5 here. So that changes then the formula to Fe2S3. Because the subscript was not a whole number here, the 1.5, we had to multiply by 2 to get a whole number. And so the empirical formula would be Fe2S3, which is probably also the molecular formula. So that's how you find the empirical formula from reaction data. Let's go through some concept check here and practice this. So there are 2 problems in this concept check, and we'll start with A. You perform elemental analysis and determine that a sample consists of 0.0806 grams of carbon, 0.01353 grams of hydrogen, and 0.1074 grams of oxygen. Determine the empirical formula for the compound. So we know we have 3 elements in that formula, and we are given the masses. And because we are given the masses, we can directly calculate the moles for each using the molar mass of carbon, of hydrogen, and of oxygen. So let's start with carbon. So you take its mass, 0.0806 grams of carbon, multiply by 1 mole of carbon over 12.01 grams of carbon, because that's the molar mass of carbon. And we want the grams on the bottom and the mole on top, so that we can cancel the given unit of grams. In the calculator, it's 0.0806 divided by 12.01, and the calculator answer is 0.006711. Yeah, we kept 4 sig figs here. That's because some of the masses have 4, so I wanted to keep it the same. So it's fine here to keep 4 sig figs. So that's the number of moles of carbon. Hydrogen, you take its mass, 0.01353 grams of hydrogen multiplied by 1 mole divided by 1.01 grams of hydrogen. That's the molar mass of hydrogen. Written as a conversion factor with the grams on the bottom, so that we can cancel the units of grams of hydrogen. And so 0.01353 divided by 1.01 is 0.013396, etc. Here, okay, I keep more sig figs than I need, but that's because I wanted to make sure we get the right answer there. So final mass, the mass of oxygen, 0.1074 grams of oxygen. Again, multiplied by 1 mole of oxygen divided by 16.00 grams of oxygen, because that's the molar mass of oxygen. We put the grams on the bottom so we can cancel units of grams of oxygen. And we get this answer, 0.0067125 moles of oxygen. So we have our moles. Now we can write the formula with all these numbers as subscript for each element. So it looks like this. And now we will divide all the subscript by the smallest of the subscript. And the smallest one is the one for carbon. It's 0.006711. And so if you divide all of them by this, you will get a ratio of 1 for carbon, a ratio of 1 also for oxygen, because you see that these 2 are very similar. And for hydrogen, it comes down to a 2. So it's C1H2O1, but the ones are implied when you write a formula, so it's coming down to CH2O. 1 carbon for 1 oxygen for 2 hydrogens. That's the ratio of each type of atom in this empirical formula. Let's do example B now. You perform elemental analysis and determine that a sample consists of 56.58% of potassium, 8.69% of carbon, and the rest oxygen. Determine the empirical formula of the compound. So here we are given percentages, and that's percentages by mass. So you want to assume that your sample of the whole compound is 100 grams, and then you convert the percentages into mass. So assume that you have a 100 gram sample, and then the masses of the element in grams will be, you take the percentages and change them into grams. So that's going to be 56.58 grams of potassium, 8.69 grams of carbon. And remember, it said the rest is oxygen. So that means you take 100 minus the other two masses to get the mass of oxygen. So 100 minus 56.58 and minus 8.69, it's 34.76 grams of oxygen. So now we have our three masses for the three different elements. So we can find the number of moles for each. So let's start with potassium. 56.58 grams of potassium multiplied by 1 mole of K divided by 39.10 grams of K. That's the molar mass of potassium. We write it such that the grams are on the bottom, so we can cancel units of grams of potassium. And we get this number of moles of 1.447 for potassium. Next, you do carbon, 8.69 grams of carbon multiplied by 1 mole of carbon divided by 12.01 grams of carbon. That's the molar mass of carbon. Written such that the grams are on the bottom, so we can cancel the units of grams of carbon. And we come to this number of moles of carbon, 0.7236. Do the same for oxygen with 34.76 grams of oxygen multiplied by 1 mole of oxygen divided by 16.00 grams of oxygen. That's the molar mass of oxygen. The grams of oxygen cancel, and the number of mole is equal to 2.1725 moles of oxygen. Next, you want to write the pseudo formula with those numbers of moles as subscript. So K, 1.447, C, 0.7236, and O, 2.17025. So that's the pseudo formula. The next step is to divide each of these subscript by the smallest one. And the smallest one is the one for carbon, 0.7236. So we will divide all of them by 0.7236. So when you do this for potassium, for K, it comes down to a 2. Carbon, it's a 1. And oxygen is a 3. So K2C1O3. The 1 is implied, so we remove it, and it's K2CO3. And here you recognize potassium carbonate. So that's the empirical formula, and that's also the molecular formula in the case of potassium carbonate.